Welcome back, everyone. Today we're going to be proving these three identities here, which are the cosine double angle identities. So what we're going to do in order to prove actually all three of these is first we're going to recall the cosine addition identity. So recall that in general, cosine of a plus b is equal to cosine a cosine b minus sine A sine B. And then what I'm going to do next is I'm going to apply that to what would cos A plus AB? Because keep in mind that 2A is the same thing as just A plus A, right? Multiplying a number by 2 is the same as just adding it to itself. So therefore, cosine of A plus A, based on this formula, would be cosine A cosine A minus sine A sine A. And that means that cosine squared A minus sine squared A is equal to cosine A plus A, which actually I should mention here, cosine A plus A is just the same as cosine 2A is equal to that. And there we go. Now we also want to prove that cosine 2a is also equal to 2 cosine squared a minus 1. So we can do that, by deriving this answer here. We've already proven now at this point that cosine 2a is equal to cosine squared a minus sine squared a, like that. Now, if we were to add in 1 here, we can recall also from the Pythagorean identity sequence that cosine squared a, so let's recall that cosine squared a plus sine squared a is equal to 1. And so because that's the case, that also means that cosine squared a is equal to 1 minus sine squared a. And then if we sub that into what we have here, we're going to get that cosine 2a is equal to 1 minus sine squared a minus sine squared a. And then we can just combine these two together, right? This one and this one, to get that it's 1 minus 2 sine squared a. And there we go. There's that one. Now let's do the cosine version of that. So once again, we're going to start with cosine 2a is equal to cosine squared a minus sine squared a. And then also, if we go back to the Pythagorean identity, if we want to solve for sine squared a, we can get that sine squared a is equal to 1 minus cosine squared a. So therefore, we're going to have cosine squared a minus sine squared a, which in this case is 1 minus cos squared a, like that. Then I'm going to use the distributive property to distribute the negative through. So if I do that, I'm going to end up with cos squared a minus 1 plus cos squared a. Then when we add up the cos squared a's, we get 2 cos squared a minus 1. So there we go. So we've now proven all three of those, which is really good. Any questions, please leave them in the comment section, and we'll see you for the next one.